All right, welcome back. We are looking at how to calculate mechanical advantage. All right, mechanical advantage is a ratio of force produced by a machine to the force applied to the machine. It compares the size of the load force to the size of the effort force. Okay, so if I was going to show that to you here, why isn't it working? There we go. So the mechanical advantage is the load force, we call it FL backwards, and then effort force, FE. All right, so looking here, this is an example of how we would use this calculation. Okay, so I have a fixed pulley may have a mechanical advantage equal to 1. So for example, to raise a flag up a pole, the groundskeeper uses an effort of 200 newtons. The load force of the rope and flag is also 200 newtons. So we're going to use the mechanical advantage, the load force, and the effort force. And so when we put this in here, the groundkeeper is using 200 newtons, that's the effort force, and the load force is the rope and flagpole, or in the flag. So that is 200 newtons. So when we divide this, we end up with 1. The pulley changes the direction of that force needed, and it makes it easier to do that work. Another example, if we're talking about first-class levers here. So for example, John and Jane use a 1 meter long stick to move a large bale of hay. They apply 1,000 newtons to the stick. The load force of the hay bale is 3,000. So the load force is going to be 3,000 and the effort force is 1,000. And then we divide, and that's 300. So the mechanical advantage is 3. The lever multiplies the applied force by 3, basically, to make it easier for us to move. Okay, there is another way to calculate mechanical advantage. So if you think about what we already learned about work, work is equal to force multiplied by distance. Okay, so if we're looking at the mechanical advantage, we can also use distance. So far we have just looked at mechanical advantage as a ratio of forces, but a similar ratio uses the effort distance and the load distance. So we could have a formula that is mechanical advantage with the effort distance on top and load distance on the bottom this time. So in our last example, the effort was on the bottom, the load was on the top, but when we're talking about distance, it's opposite. Something very important to remember. So our example, John and Jane decide to use a longer pry bar. This one is 3 meters in length. They place the fulcrum at 0.5 meters from the large stone. They push down on the opposite end of the pry bar, and it's 2.5 meters from the fulcrum. What's the mechanical advantage? So the mechanical advantage is the effort distance divided by the load. So their effort is here, the 2.5 meters from the fulcrum. They push, because it says they push down on the pry bar, so that's where the effort is. So it's 2.5 meters from the fulcrum, so that would go up here in the effort distance. And then they place the fulcrum from 0.5 meters from the stone. So it would be a mechanical advantage of 5. Okay. The longer that lever is, the greater the mechanical advantage is going to create. So mechanical advantage of a bicycle is usually less than 1. The output forces are actually smaller than the input forces. So how can bicycles be so useful if they have such a small mechanical advantage ratio? The output forces cause the bicycle to move faster than a person can normally walk. So the advantage gained is actually in speed. As well, the overall amount of forces to pedal a bicycle is not very large at all. So the person on the bicycle gets to enjoy speed and comfort for the work they've done. Any advantage gained by a machine comes with a trade-off. So for example, An increase in force applied may require a longer distance traveled to complete the work. An inclined plane helps to lift heavy objects up to a certain height. However, the distance traveled along the inclined plane is usually much longer than the height. This makes the job of lifting easier, but the distance traveled longer.